So thank you very much for the invitation, and I'm really sorry that I haven't been able to travel to see you all. I see so many familiar faces in the audience, and it would have been really nice. And since I'm online and not there to maybe discuss later, please feel free to interrupt even during the talk and ask questions. I wouldn't mind at all. So what I want to talk about today is just give you a flavor of some new kinds of searches that have become quite popular over the last few years, and in particular, why these searches can be useful when discussing dark matter and what their signatures should be. As we all know, there has been now a huge amount of evidence from cosmological observations that there is something that looks very much like dark matter, and there have been decades of searches of different kinds to try and look for what this dark matter might be. And two of those categories of searches are these so-called direct detection searches, which are fixed target experiments, or indirect detection searches, which try to put telescopes, say, for example, in space and try to look at products of annihilations of dark matter in places where there is a lot of dark matter expected. What I'm going to talk about is a complementary approach that does not rely on any of these astronomical uncertainties, but what if we could produce dark matter or something that is related to dark matter directly at the collider? So that is what this talk is going to be. And what I would like to answer are these four questions. So the first one is, why does dark matter predict long-lived particles at all? What kind of long-lived particle searches exist? What kinds of things are missing once we have dark matter concentrations into account? And if we have completely different unexpected dark sectors, can we have some LHC signatures of those as well? And then finally end with some future directions. So let's start right away. So we want to answer, first of all, the question, why do we need LLPs at all? Okay, so let's go back and recap a little bit of how we have designed our LHC searches for dark matter so far. And they rely on this very minimal picture where you have a neutral, massive, stable particle, which is in equilibrium with standard model at the early universe. As the universe expands, this reaction slowly goes out of equilibrium, and then finally you have a situation where your dark matter freezes out and gives you a density that's observable today. So this was known for a long time. And if you have dark matter in equilibrium with the standard model, that means there must be some kind of interaction. If there is some kind of interaction, and you can write down, say, for example, a theory for it, you can just reverse it and try to produce dark matter at the LHC. So this was the idea. Since it's neutral and stable, it's going to be invisible. None of the detectors are actually going to interact with this object. So you need something extra for this invisible thing to recoil against, which is why you come up with these so-called mono X searches, where X can be a jet or lepton or Higgs or whatever, right? So that was the idea, and that's what people have been looking for a long time. Okay, making the theory more concrete, adding some more numbers, people came up with this idea of WIMP miracle, where the natural scale of the mass and coupling of the dark matter should be similar to weak interactions. And people also discovered that you can have a picture where you have an extra particle that accompanies your dark matter. And it's not only just dark matter to standard model annihilations, but co-annihilations that together set your relic density. And in that case, you can have an extra particle, which I denote here by M, which usually has some standard model charges, and therefore interacts more strongly with the standard model. So this is also not new at all. People have known this for a long time. But if you have a model like this, then what you can do is, again, reverse this process of annihilation and then try to produce these particles. And because this new particle M has standard model couplings, you can produce them at the LHC, either singly or in pairs. And then it decays again back based on the same vertices into dark matter plus something else. So again, you have very similar familiar signatures. So you have missing energy and you have some associated particles. So this has all been quite well known. And the advantage of this kind of modeling was that you had multiple channels, so to speak, in which you could have seen dark matter. So you could have seen it in direct detection, indirect detection, and colliders, because pretty much all of these same Feynman diagrams dictate what your signal strengths in each of these are going to be, right? And so here are some popular models that people have studied for decades, where you could have seen something. However, as we all know, the situation right now is that we have very, very strong limits, both from direct detection and from LHC, where we don't see anything in these expected channels. Okay, so on the right, you see in particular what the missing energy spectrum looks like at the LHC compared with what we expect from the standard model, and it all looks it agrees very, very well. So if you're an optimist, you're very happy with the state of art calculations. If you're a pessimist, then you're unhappy with not seeing anything, right? So either way. So people, of course, have started asking, is this really the only way to get the right density of dark matter, right? And there has been a lot of work on that direction as well over the last 50 or so years. And we have moved away from just this freeze out picture to having both non-thermal mechanisms of getting the right relic density. One of them is this freeze-in, as well as more complicated mechanisms. So co-annihilation was one step more complicated than just normal annihilation, but you can have further complications as well. And in fact, now people have started publishing these sort of diagrams where by changing couplings, you can move from one kind of mechanism to produce dark matter to another kind of mechanism that produces dark matter. So that's why I put the phase changes in quotes. So it seems that there are many more options now for getting the right dark matter density. And so we should be reevaluating what our signatures of dark matter at the LHC can be. So the first one that I want to talk about is co-scattering. So the idea for this is very similar to co-annihilation. So you have a diagram of the dark matter with this M particle, which I'm going to call the mediator particle, as before, but neither of these is efficient enough to get you the right relic density. So what happens is the dark matter interacts with the standard model path and sort of upscatters into M. And then because the annihilation of M is very efficient, you have a reduction of your dark matter density via that particular channel. So in this case as well, what happens is now you're no longer producing dark matter directly, but because you have these mediator particles, which are charged under standard model, you can produce them at the in collisions. And because the parameter space where this works is cases where this coupling between the dark matter mediator and standard model is very small, that results in this mediator being sort of long-lived. And so it decays back into the standard model and some dark matter. And this is the decay that you want to observe. Okay, so that's the first case. The second case is that of freeze-in, where you start with no dark matter in the early universe to begin. You have this mediator particle that freezes out to a very small number density. And then over time, later on, either you have decays of these mediators, or you can have mediators decay, interacting with the standard model to slowly produce dark matter over time. Okay, so this is the freeze-in mechanism. And again, since you have this extra particle with standard model charges, you can produce it directly. And again, because the coupling scales where this works is very, very tiny, you have long-lived mediators, which decay into some multiple particles at the end. So in both these cases, what you see is that because these couplings are extremely small or even feeble, you don't really have a signature in direct detection or in indirect detection at all. So if indeed you produce dark matter via these, if the universe produces dark matter via these mechanisms, then perhaps the only way to confirm these would be via producing them directly at the collider. So what I want to convey in this part essentially is that if you expand your models of what is allowed for dark matter, then you automatically also get new kinds of signatures at the LHC. So just to summarize, I've been talking about these long-lived mediators for a long time. So what are the ways to get long-lived particles? So essentially, long-lived means very small decay width. And to get a small decay width, there are three ways of doing that. You can either have very small couplings, or you can have a three-body decay or n-body decay with heavy intermediate particles in the middle. Or you can have a compressed spectrum, which gives you very little phase space, which gives you small decay width. Okay, so these are the ways of getting a long-lived particle. And then to produce the long-lived particle in the first place, either that particle itself needs to have either color or electroweak charges, or it needs to be produced in the decay of another particle that has some SN charges so that it can be produced. Okay. So this is just a summary, and we can look into the vocabulary of what kind of searches exist currently. Okay, so I've sort of categorized the searches into two. So the first one I call displaced, and the second one I call prompt, even though it's in quotes. So the idea of a displaced lepton is a lepton that is produced with an impact parameter away from the interaction point. So it sort of looks like a track that doesn't actually go through the interaction point. Then if you have invisible particles that decay into multiple particles that form tracks, you can have vortices that appear later in the tracker. So something like displaced vortices. And then based on what kind of particles are making the tracks, you can have different kinds of vortices. Okay. Then similarly, if the particle decays further on in the calorimeters, what happens is you will still have some deposits there, some energy deposits, and you can make jets out of them, but they don't look like normal QCD jets. So you can have what are called either displaced jets or emerging jets, trackless jets. There are various definitions based on B tables. The other possibility is that the long-lived particle itself carries charge, electric charge in particular. And in that case, if it is long-lived enough, then it can give you a heavy charge track that exits your detector. Or it can decay somewhere in the middle. And in particular, if it decays right before the outer edge of the tracker, it gives you what is called a disappearing track signature. So we'll look at, so these are essentially the kind of signatures that are possible if you have long-lived particles. And each kind of dark matter model will predict a different kind of signature. Okay, so for example, for freeze out or co-annihilation, what we had was invisible particle plus maybe some standard model, plus a particle with standard model charges, and that gave you either leptons plus met or jets plus met or a vector boson plus met kind of signature. So well known. Now what you have is you have long-lived particles that can give you heavy tracks, or you can have displaced vortices or displaced leptons, or these odd emerging jets or semi-visible jets. And I've added another box to the top, essentially, which talks about hidden gate symmetries, which is the idea, since our visible sector is essentially made up of composite particles, protons and neutrons. If the dark matter sector is also some sort of composite sector, which results in similar production of dark side jets in the LHC, then they can also give you very similar signatures. So even though it's not typically a long-lived particle scenario, it gives you pretty much the same signatures. So I've put it on the same slide. So this slide is to give you an overview of what kind of signatures are out there and what kind of assumptions lead you to what kind of signatures. Okay. So if you want to propose a new model in the LHC era, it's not a simple story of just writing down the Lagrangian and that's the end of the story. But you actually need to do some extra work, and that work involves basically identifying the corresponding LHC production mechanism, maybe making a simplified model, making some benchmarks that the experimentalists can study, and then provide a proof of concept search strategy to say that this is actually really possible. So in the rest of the talk, we're going to basically understand how to do this last bit a bit better. And then we are going to talk about what kind of gaps still remain and what needs to be done. Okay, so let's come to part 2, which is about existing searches. So I already showed you a cartoon diagram of what the searches look like. And what I want to do now is to tell you about how, as a theorist or a phenomenologist, you can use the results from the searches for your own model building, right? So what both Atlas and CMS do is they provide you with results in this form, where you have 95% upper limits on cross sections for based either on mass. So in this case, it's just a charge track search. So the only assumption is that the lifetime is long enough that the track extends all the way out. And so for given the mass of the particle, you can have an upper limit on what kind of cross section is allowed for such a mass and such charge, right? So there are limits from both Atlas and CMS. As the search becomes more and more complicated, the limits also become more and more complicated. So this is the second case, is this disappearing track search. On the right-hand side, you have a cartoon of what this search actually does. So you have a charged track, which is hitting the inner layers of the tracker detector, but then it suddenly decays in the middle, and the decay product is too soft to be detected. And so the track, which should have continued, doesn't continue anymore, right? So this is the search. And for this search, you can see, so the cartoon is from Atlas, the limit is from CMS. So this is the full run-to limit that they have published. And based on their particular benchmark model, they have excluded certain masses and lifetimes. Now, if you change the production model, what changes is, for example, your boost of production, and it will change maybe significantly what this exclusion looks like. So if you have the exact same kind of model, or a model that can be one that has one-to-one correspondence with what they use, then it's very easy to use this data directly. But if you have something even slightly different, it might not be as simple. Okay, so we'll make this point a bit more clearer here. So this search is for displaced leptons. It looks for two leptons in the same event, which both have some non-zero impact parameter with the interaction vortex. Okay. And this is the same study, and you have two different benchmark models that the same experiment has used. And you can see that the lifetimes that they are able to rule out varies really greatly. So in this case, where they have chosen a scalar with leptonic quantum numbers, with quantum numbers the same as either muon or electron or tau, you can rule out maybe something a little bit more than 10 to the 2 centimeters. However, if you produce your leptons not from a scalar with just electroweak numbers, but with strong quantum numbers, then you get the double advantage, first of all, of having extremely large cross sections, because LHC is a PP machine. And secondly, extremely large boosts, because this guy is very likely to be heavy.
Nishita, you have 10 more minutes.
Okay, thank you. So, so putting that together, you see that your limits can change very widely based on what your initial assumptions are. Multiple tracks emerging from the same point. And again, this is a very nice presentation where, based on the number of tracks and the mass of the reconstructed vortex.
Nishita,
yeah.
The line got disconnected for a while. So can you repeat?
Okay. Can you hear me now?
Yes.
Okay. Yeah, sorry about that. Yes. So I was saying that what Atlas does is that they present their results in this very nice and reusable format, where they give you the number of observed events based on the mass of the vortex that has been reconstructed and the number of tracks the vortex has. So these numbers that you see on the plot are actually observed numbers. And then this dotted line is their discrimination between signal and background. So using that, they also place upper limits on cross-section for various lifetime. As you can see, this actually assumes the mass of the producing particle. So it's a three-dimensional plot. So you have to basically choose what two directions are important to you and make your plot in that way. So this, I hope, gives you some idea of what kind of limits are available from experiments, and also makes it clear that it's not always completely trivial to use this data to decide whether something that you are writing as a new model is actually feasible or not. And for that, what we do is we have this whole reinterpretation framework where we try to reproduce the experimental analysis as closely as possible, making use of the efficiencies that the experiments provide, and try to these are all publicly open. So one of these codes is Checkmate, which I work on. And so hopefully this will allow other people to make use of these published results for their own models. So putting all of this together, so all of these searches can be applied to the same model. So first of all, we need to write a simple model to test. So the simplest model that you can think of is a model where you have two new particles, a scalar phi and a fermion chi, which serves as your dark matter. And then you have some kind of Yukawa coupling between them. Okay, and the phi carries some quantum numbers so that you can write this coupling, which means you can produce it by Drellian. And then you can apply all of these search limits and ask if such long-lived scalars are still allowed. Okay, so you can see that different searches give you different kinds of limits, and in particular, it's possible that all the searches that have been performed so far don't actually exhaust all possibilities of lifetime or coupling. So there might be obvious gaps, and those gaps can be filled by thinking of new searches. So in this particular case, what is happening is you have some track searches here and displaced lepton searches here. And if you have an intermediate region where you can have a kink track where you have identify both the track of the original particle and the track of the lepton, then you could fill the gap. So that's a way of identifying what is missing. So instead of having an electroweak charged scalar, if you have a strongly charged scalar, then you can have displaced vertices, and you can reinterpret displaced vertices searches in the same way. So given a realistic model, so here we actually wrote down a model which gives you the right dark matter density via freezing. So it's a very similar coupling to before, except now your dark matter is the scalar and your mediator is the fermion, and you can produce the fermion via Drellian. And you can see that mixing and matching all of the searches, you can basically exclude a huge amount of parameter space that would be viable. Okay, so I'll talk a bit more about identifying gaps. And for that, I want to talk about this, again, a very simple model where you have two fermions, a standard model singlet and a standard model triplet, and the neutral parts of them mix to form two states. Okay, so if you produce the charge component of the triplet via Drellian, again, there are only two decay modes open. One is to the mixed low mass state via an off-shell W, and this has a small width because the mixing is small, or to the nearby lying state, which is again has a small width because it's very, very compressed. So in this case, if you produce the charged partner of this triplet, then it's almost always going to be long-lived. Okay, so the expected signatures from this are, as usual, what you would expect from usual decays if this was just a standard charged triplet fermion, but also now in our case, where you can have some extra displaced or long-lived similar signatures that are displaced or long-lived. Okay, so what we did was we tried to investigate whether this kind of a model would be visible in current searches. So the first thing to do is to ask if your standard SUSY searches, which look for these kinds of triplet fermions, are sensitive to your model. And we found that at the time when we were doing this study, it ruled out things up to about 200 GeV, so 220. And in particular, if you require the dark matter density to come out right, then that also fixes how much compression you need to have between this triplet and singlet state. So you cannot have arbitrary mass difference, because then it doesn't give you the right reaction rates. So that sets also your delta M, the mass difference. And putting those together, we asked, does the displaced lepton search actually capture this kind of a situation? So the displaced lepton search, I told you, look for two displaced leptons. Okay, so there's an electron and a muon, and this is the displacement that the search requires. So in particular, the signal region 3 is the most sensitive, and it requires both of them to have displacement of 1 millimeter or more. Okay. However, to identify said electrons and muons, both of them have been required to have a PT of about 40 GeV in the search, right? So if this delta M is artificially put to 40 GeV, then it has a very nice range of lifetime that it can exclude. But as soon as you make the mass difference to what actually dark matter considerations require you to do, you see that the search loses all sensitivity. Okay, so R is the ratio of what is ruled out by the experiment to what is predicted from our model. So you see that this whole curve lies entirely below this line of 1. So what can you do? So first thing what we did was we tried to estimate what the background would be if you change the cut from 40 to 20. So we did some sub-calculations. I won't go into the details of this. You can based on the shape, you can calculate essentially how much the background would grow. And what we found was that the background is so huge, it's several orders of magnitude bigger than the signal, and there is no hope of getting anything. So, however, since there is really a signal with significant characteristics, you can actually design neural net-based search. So here is where the proof of concept idea comes in. So we designed this search, found out some variables that are useful, and we proved that in fact you can do such a good job with this neural net that you can actually recover the full sensitivity after run 3 of the LLC. Okay, so I'm sorry this was a bit fast, but what I wanted to bring across was that there is one obvious gap here, which is that when particles are both soft and displaced, they sort of fall in the gap, and you cannot really find them. And you need to have new searches, maybe even new triggers, to be able to find these kinds of dark matter models. Okay, so I won't go into the detail of this last part. So I wanted to give you one last new idea that's been worked on nowadays, which is this idea of dark shower, where the idea is that if your dark matter is actually a composite object like protons or neutrons, can you have some kind of signatures at the LHC? And for that, what people have come up with is the simple idea is that you have a heavy mediator and some hidden sector quarks. These are not QCD quarks, but these dark quarks. And then you can have dark shower and hadronization. And then because you have this mediator, some of these dark side mesons can decay back into standard model and thus give us some visible signatures. Okay, so there has been one sort of simple search for such mesons. This is this dark pion that they have been looking for. And they constructed a model where they put this kind of a mediator that is a scalar that is charged both under the dark gauge group as well as QCD, so you can produce a lot of them. So the question we are, okay, so let me just summarize this slide in one sentence and then I'll end. Okay. So the question you can ask is that, is there something you can do? So as you can imagine that there is a huge phenomenology possible by changing the N of SUN, how many flavors you want, blah, blah, blah. So can you encapsulate this in a simple way? So it seems that it is possible because after all, what you see is really jets in the end. So it might be possible to write a phenomenological model that encapsulates all of this. Okay, so I'll skip this and only say that there are more gaps to be explored. For example, third generation fermions in LLP decays and so on. And there is an LLP working group that has been working on all of these things. And you're welcome to attend our workshops. And thank you.
Thank you, Nishita. It was a nice talk. Now you have some time for a few short questions. Yes.
Hi, Nishita. This was a beautiful talk. Thank you. I have a comment essentially regarding the different possibilities of, FIMP and WIMPs giving rise to this long-lived particles and MET and so on and so forth. I just wanted to comment that if you have a FIMP-like model where a neutral heavy mediator is decaying to dark matter, that decay can even also escape the detector and give rise to the missing transverse momentum and missing energy. So the boxes and the connections that you did just had that one link missing. So that's what I wanted to comment on. And
okay, yeah, thanks. Yeah, you're right. You're right. If it is long-lived enough, then it still looks like missing ET. But yeah, then it looks like what we know. So I did not put that line, but yes, maybe it should be there.
Yes,
thanks.
yes. Thanks.
Nishita.
Hello. Yeah. Hi, Nishita. This is Nishita. Thank you for the nice.
Yeah, hi.
I don't know whether this question should be addressed to an experimentalist, but in your slides, you show that CMS did these displaced lepton searches for, let's say, tau or muon going to gravitino. So my question is there a problem with the detector sensitivity or cut analysis that they are only considering gravitino and not a neutralino? I mean, for example, the tau and LSP can decay to tau and neutralino as well. And
yeah. So first of all, my impression is that what they really wanted was the cleanest possible model, right? And so they found. So in my experience, the way this works is that they talk to the theorists that they know and ask for a model that satisfies their requirements. So you want a clean model that is physically probable or physically self-consistent. That gives me one displaced lepton on each decay leg and nothing else. And so I guess somebody came up with this model and they told them that this is it. But of course, you can make more complicated models with taus or with more NLSPs and so on, right? So yeah, it's not really, I don't think it's theory motivated in that sense. It's motivated based on what signature you want.
yeah, okay. So the one that you have already done, for example, you showed a neural network study where you are reducing the initial cut for the displaced leptons. That can also be done in case of this kind of scenario where the LSP is a neutralino and not a gravitino.
Yes. So the only situation there, I mean, yes, of course, you can. I mean, it's not really dependent on what the extra guy is. It really depended on what the PT of the displaced lepton was. So if you have a scenario that gives you that kind of expected lepton PT, then why not? Of course.
Thank you.
Nishita, hi. In the slide that you mentioned, the delta M for the, I think it was slide 31. Can you please go back to that slide?
Yeah. Is this one
basically
or
progressively
this one?
reduced the mass range to down to 20 or 10 even.
Yes.
Delta M, that delta M plot.
Yeah.
So
this is the one, right?
Yeah. So my question is like, how like realistically can you probe for delta M's of the order of say 10 GeV when we are using, like say, lepton triggers that have transverse momenta cuts, like hard cuts on hardware of the order
Right.
of 20, 25 plus. And in
Yeah,
fact,
so it's
as a
very,
trigger
very,
person, until unless
yes.
you pre-scale the triggers or use Spark dataset, it's not realistically possible to maintain triggers for such a low threshold. So how
No.
like feasible
No,
is that?
yeah. Yeah, I absolutely agree. So what this plot in fact tells you is that because the trigger requirement is so high, you basically lose sensitivity at small delta m, right? And this happens because you still have a small number of events that give you a large PT of the leptons because of initial state radiation or other some such effect, right? So you have something else that is going on in the event that gives the lepton the required PT to pass the trigger. So if you want to have a situation where you won't get this extra stuff, then basically you will have no sensitivity at all given current triggers. So there are several options that people are debating. For example, using multiple. So all of these things have multiple particles happening at the same time. So rather than having a single lepton trigger, you can have maybe a multiple lepton trigger, and then reduce the PT threshold of the overall thing, or maybe start with a photon trigger instead of having a isolated good electron, or blah blah blah. I mean, okay, I'm not a trigger expert, so I won't be able to tell you the details. But there are definitely ideas like this that have been floating around, and there has been a trigger white paper from the LLP working group trying to collect all of these ideas together.
Any other questions?
So, Nishita, this is Rohini.
Yeah.
Thank you very much for the very clear talk. I wanted to ask you that you have talked here about, this is singlet-triplet is essentially, if I may,
Yeah, of course. We know.
Right.
Yes, I know.
Now, the question I have is that if one takes displaced jets instead of displaced leptons, have you looked at that? I mean, does that add, some more, region that you can probe?
Okay. So the answer to that is actually multi-step. So so we've looked at displaced vortices, but not displaced jets as such, because it seems to be a bit harder to translate the displaced jet criteria into reinterpretable stuff. So I tried it when Atlas came up with its trackless jet search. After that, I have not looked at it again. So maybe there is some improvement, and I should definitely look it up again.
The reason I asked is that in the last recent searches, Atlas and CMS, I think both perhaps, have started looking at when your charginos and neutralinos, not necessarily give leptons, but give jets. And that, of course, increases your sizes of the event sample, of course, increases the background. Triggering is an issue.
Yeah.
And I'm just curious whether you could repeat this exercise now with the newer search strategies where they do have jets in the final state. They use leptons.
Yeah, I'll definitely take a look, because I mean there are multiple things, right? There are so many jets from just standard model events, so they probably have very strong conditions about shower shapes and things like this to make sure that they capture the right things. I'll definitely take a look at it. Yeah, thanks for pointing that out.
Any other question? Okay, so if not, so let us thank the speaker.